Alright, so far we have already seen how vectors form a tangent space. So if you take any spherical surface as your manifold, then at any given point your tangent space at P is tangent to this point, while if you take another point Q, you'll have another tangent space, and vectors are well defined on the tangent space. Here also the vectors are well defined on the tangent space. But these vectors as yet cannot be compared with vectors which form a tangent plane at another point Q. So here these vectors, because this part of the vector space you can add, subtract the vectors, you can multiply any number to a vector, it's well defined. But there is no way as yet how to compare a vector here and a vector here. So far we don't know how to compare a vector belonging to the tangent space at point P and a vector belonging to the tangent space at point P. We have no clue as of now how to compare the two vectors. Alright. And as I said yesterday, that now that we know how the abstract vectors are related to its components, provided you have a notion of chart or a coordinate system, and similarly the one form, once you have a coordinate basis, you can talk in terms of its components. So now we are going to completely deal with components alone. I'll not use the abstract language of vector existing just like that without ever referring to its components, or a differential form, or a tensor. We have seen what is its relation with its components. Yesterday we have discussed. So from now on I will be using the language of tensor calculus. Where my abstract vector, I'll assume that we have chosen a coordinate system. This is equivalent to its component V mu. Similarly, a differential one form is equivalent to a contravariant vector components, and so on. And arbitrary tensor. These are all fields. This is defined at a point. So arbitrary tensor, R contravariant indices, S covariant indices. We will be now talking only in terms of its components. Yesterday we said that these are actually objects, don't depend upon your coordinate system, but from now onwards we will deal with only components. And these are fields, they are defined at points. So at P you will have a value, at another point Q you will have a different value. But as I said, we have not introduced how to compare a component of a vector at point P and the components of a vector at point Q. So far we don't know. Good. How do we find out how to compare the vector? For scalar, it's not a problem. So imagine you have a coordinate x mu and nearby another coordinate x mu plus dx mu. The moment, it doesn't matter whether I am talking about a Riemannian manifold or a pseudo-Riemannian manifold. Riemannian manifold, which mathematicians dealt with, the signature is plus, is the Euclidean. Positive definite. And in Riemannian manifold, the magnitude of a vector is 0 only for a 0 vector. But because special relativity told us that the real manifold, that means for physics, it is not Riemannian. You have vectors whose magnitude is 0, although they are not 0. Namely, those vectors which are null vectors, the tangent to a light ray. And that is something which came from physics. Mathematicians never thought that such a thing will arise in the physical world. And that's the reason I am now adopting instead of I, J, K, I am using mu. And at the back of the mind, mu is going from 0, 1, 2. It can go up to arbitrary number, but for our space-time manifold, mu is going from 0, 1, 2, 3. 0 is time and 1, 2, 3 are the spatial indices. But you can talk about arbitrary number of spatial dimensions. So here, if I have a pure scalar field, f, if f is a pure scalar field, x of alpha, and here it will be f of x alpha plus dx alpha at this point. I have no problem comparing a scalar field. A scalar field, what is a scalar field? Scalar field at every space-time point is a number. If it's a real scalar field, it's a number. If it's a number here, it's another number here, I just subtract from this number the original number, then I have a notion of df. So df, by definition, what is df? df is f of x alpha plus dx alpha minus f of x. There is no problem in comparing a scalar field because it's a number. You take the number here, from that you subtract the number here, you get a df. But vectors I can't do it because I haven't told you how to compare the vector on the tangent space at point P and the vector belonging to the tangent space at point Q. Remember, this is your TPM, this belongs to TPM and this belongs to TQ1. So I can't add vectors belonging to one tangent plane with another vector belonging to another tangent plane. So far, I have not told you how to do that. So the question is, how do I find the differential of a vector? Differential of a function is not a problem even in curvilinear coordinate system. So differential of a function d of f in curvilinear coordinate system is just the ordinary differential d of f. I want to know what is the differential of, first of all, a vector component v of p. That means, how do I know how to get the real difference between a vector here and a vector here? Because I can't subtract. Vector at another point and vector at this point, if I just subtract, it won't be a vector. What is the best way to do it? So that's what people like Riemann, etc., they thought about, that how do I know the differential? I mean, here there is a vector field, here there is a vector field. Even if these two vectors are same meaning what? This is an important point. Same meaning they have the same direction, same magnitude, but because I am using curvilinear coordinate system, their components will be different. Okay? I can give a simple example where the same vector, if you choose polar coordinate system, the components will be different. So imagine a plane. Okay? If you have a plane, then consider a vector at the origin here. So remember, this is your x, y in the Cartesian coordinate system. So this vector, what component would it have? If its magnitude is v, what will be the component of this vector here? Your v vector in xy coordinate system will have what component? This vector?
0,
0 because it has no x component, 0 and v. Alright? Agreed? Now the same vector in spherical polar coordinate system. Suppose I take, not spherical, it's a two-dimensional polar coordinate system. Now consider another vector. Take another vector which is parallel to this vector, v. In the Cartesian coordinate system, what will be the components of this vector? So this is my, so this was vector v1, this is vector v2. For v1, you told me the components. For v2, what will be the components in Cartesian coordinate system?
0, a comma v.
Some a.
I'm not talking about where it is. Say, let's say this is, its base is at A. Here the base was at origin. I'm simply asking the components of V2 in Cartesian coordinate system.
0, comma
0 V is the same. So by looking at the component or by looking at the figure, you know those two vectors are parallel and the components are also same. Parallel vectors and magnitude is same, so the components are same in Cartesian coordinate system. Agreed with me? Agreed. But now let's go to the polar coordinate system. If you choose polar coordinate system, in the polar coordinate system, okay, in the polar coordinate system, what are your unit vectors?
r and theta.
Unit r
And theta.
and unit theta. So unit r, so your vector is unit vector r and unit theta. Unit r, from the origin, it is at every point is radially going out, unit r. And unit theta, how? It will be perpendicular to the radial vector here, it will be perpendicular here. Now the same vector, now give me the, in polar coordinate system, what are the components? The same vector.
v comma pi by 2.
V, because V into E of R is from origin it's radially going out. So component along ER is V. And what is the theta component?
0, pi by 2.
No, 0. Because theta here is tangential. It doesn't perpendicular to ER. It's 0. Okay. Whereas this vector is radially outwards. It doesn't have theta component. 0. On the other hand, the same vector meaning same magnitude, same direction. At this point, what are its components? It doesn't have radial direction is this. It doesn't have radial component, but it has theta component. So its component is 0. Okay. So this tells me that the same vector, Cartesian coordinate system, the components were same, but in r theta coordinates, the components are different. So by looking at the components, you can't say whether the vector is same or not. These mathematicians had realized long time back, and they said, therefore, a vector here and a vector here, if I want to compare, I have to have a notion of comparison. Just by looking at the components, I'll not be able to figure out whether the vectors are same. So mathematicians are, they are very smart guys. They knew exactly how to compare. So they realized that we have to, now I am going to talk about contravariant vectors. We have to, had thought that I had placed the dusters at the appropriate places. Looks like I didn't. So I have the vector field V mu at x alpha and have this, it's a vector field. So at this point, the vector field will be x alpha plus dx alpha. And I want to compare, I want to find out how to subtract, how to take the differential of the two vectors. And as I pointed out here, I cannot subtract the components wise, will give me nonsense. The same two vectors, the components happen to be different if you choose curvilinear coordinate system. So mathematicians realized the only way you can compare is to have a notion of take this vector, it's an arrow, by arrow I mean the component, I parallel transport it to this point. If I parallel transport the vector to this point, the vector at x alpha, I parallel transport it, and this vector here was like this. I parallel transport it. After having parallel transported, I take the difference. Why it is a valid procedure? Because I can add, subtract vectors at the same point. That I am allowed to do because at every point the vectors form a vector space. So adding and subtracting vectors at the same point, I know what to do. But in order to compare a vector belonging to TPM and a vector belonging to TQM, I have to have a notion of parallel transporting a vector here and putting it here. And then after parallel transporting the vector, now I take the difference. That will be my real difference of vector meaning. Real difference of scalar function is just ordinary fx alpha dx mu minus fx alpha, which is df by definition, because this is same as del f by del x mu dx. But I want to have the same thing done to a contravariant vector. Is the problem clear? This is the problem, and we have to therefore find out a notion of a parallel transport. See how mathematicians think. They simply get things out of the air. So this logic, just mark the logical train. You will see things are being pulled out of the air by magic. That's the thing, beauty of mathematical reasoning. So what I want to do is I take this differential will be the v mu at x alpha plus dx alpha minus after parallel transport. V mu of x is here and I have to add something to it, del of v mu, so that this object has been parallel transported, and this is after parallel transporting v mu to this, you have got this object, and this I can subtract. So I want to know by how much the components change when I parallel transport the vector. So what is a change in the component when I parallel transport v mu to the point x mu plus dx? I want to know this so that I know how the total components have changed. What is this del of v mu? What is this? Here closely follow the reasoning of the mathematician. People like Riemann, Gauss and all that. First of all, clearly del v mu will be proportional to by how much you have moved from here to here. It will be proportional to dx alpha itself. Agreed? If I did not move, dx alpha is 0, then no change in components is expected. So del v mu must be proportional to dx alpha. Look at the logic that mathematician is following. Agreed? It should also be proportional to the vector itself. If the vector is small, the change in the component should also be small. So it should be proportional to v beta. Agreed?
Sir, is there any reason to assume that a relationship would be linear? Like it could
Yes, because if I change it, you would expect, all these are infinitesimal changes. I am not going from x mu to x mu plus arbitrary large number. We are only talking about how, if you move a little bit infinitesimally, how much change is there. For any infinitesimal changes, the higher order effects, dx mu square, dx mu cube, they will be so negligible I can neglect them. This is a Taylor expansion view. If your f of x plus delta x, if delta x is very small, you can neglect delta x square, delta x cube, higher orders. So we know that purely from arguments of geometry and continuity, we know that change in the components when I have parallel transported the vector is proportional to v beta and dx alpha. And therefore you will say, okay, in order to make it equate, let me invent something. Let me invent a function v mu, and because beta alpha are appearing, so I will put beta and alpha on the. And remember, whenever things are repeating, it is being summed over. I don't know what this object is. It can depend upon x because these are all dependent on x. So, minus sign I have introduced so that when I finally do all the calculation, it must agree with the standard definition of this gamma mu alpha. Okay. So, in other words, purely from mathematical reasoning and continuity and the idea of infinitesimal thing, we know that when you parallel transport v mu to a point at x mu plus dx mu, the change in the components must look like this. As yet I don't know what these new objects gamma mu alpha beta are, but you will see over the lecture it will magically come out of certain very natural assumptions. That's the whole beauty of the works of starting with Gauss, Riemann and others. And people like Christopher, with this name, this is called the Christopher symbol. So one must pay also respect to other mathematicians. Right. Now, actual change in the vector field, which I am denoting capital dV mu. By the way, all these I am following the notation that is given in Landau-Lifshitz classical theory of field. So therefore, the actual change in the vector field d of v mu will by definition be v mu x alpha plus vx alpha minus v mu at x alpha, and plus delta v is this minus gamma mu. So therefore, what we have got is d of v mu plus gamma mu beta alpha by x I mean x alpha. I mean I'll suppress sometimes many of the indices. Okay. But what is v mu x alpha plus dx alpha minus v mu x alpha? What is the subject? When dx alpha is infinitesimal. So first order in dx alpha, what is this object? Exactly. Good. So this is nothing but del v mu by del x alpha dx alpha. this one. Now dx alpha can be taken common, and we have got the result that dv mu is dx alpha. Okay. Just like dv, ordinary differential dv mu is nothing but dv partial derivative del x alpha dx alpha. Here we find dv mu is this quantity dx alpha. This object is called the covariant derivative, just like it's del v mu by del x alpha. I'll introduce a symbol that this is v of mu dx alpha. This is just a symbol. Sometimes in certain books, Landau-Lifshitz books, this is same as v mu semicolon alpha dx alpha. This is a covariant derivative with respect to alpha, and sometimes, so in the standard books, del v mu by del x alpha is written as v mu comma alpha. Yeah. So symbol very often used, instead of all the time writing del v mu by del x alpha, we'll use the shorthand notation v mu comma alpha dx alpha. So comma alpha is ordinary partial derivative, semicolon alpha mu is this object, which is the covariant derivative. In Landau-Lifshitz, this symbol is used for covariant derivative. In books like Hartle's and Wald's, they use that as the symbol. So yes, so sometimes when textbooks use different notation, it can be confusing, but once for all you know what they mean, everything is placed in proper order. All they mean is this object being the covariant derivative of the vector. But we still don't know what is the functional form of the Christoffel symbol, or what does it depend on. That we don't know yet. Good. So just like ordinary differential of a vector field is partial derivative with respect to x alpha dx alpha, the real physical differential between two vector fields is, we have derived it to be this is given. What I am using the real difference, what do we mean by real difference? What we mean is, had this vector field, if v mu at x plus dx mu dx alpha was purely the parallel transported vector, what should have been the capital D of that? 0. Because it is just a parallel transported thing. But in general, vector field here and vector field there may be completely unrelated. They may not be parallelly transported. But if there is purely parallel transported vector field, then D of capital D of v mu must be 0 for a pure parallel transported object. And I will come back to that, purely something being parallelly transported. Fine. Now you will ask, all right, you have given me a way to find out the actual change in the vector field, not the component change, actual change in the vector field when one goes from one point to another, and that's for a contravariant vector field. Now you say, oh, but there are also differential forms, forms whose components are covariant vectors. How do you do it for the covariant vectors? So what mathematicians are clever and they don't want to do too much of work. They have done it for the contravariant vector field. So how do you think they will do for the get the result for the covariant vector field? Huh? Very good. Great. So we already know what is the change for a scalar field. That we know. And a covariant vector can be contracted with a contravariant vector and it will be a scalar. That we have already seen when we were doing the differential geometry. So they will say, okay, good. You take a covariant vector field whose components are u mu x alpha. And we already know that v mu u mu at x is a scalar field. Scalar meaning it doesn't change when we make coordinate transformation. That we have seen when we are doing the differential geometry. We saw that the components, when it's an inner product, it comes out of df comma v vector, and it doesn't depend upon which coordinate system you are choosing. So they will say that this is a scalar field, and therefore capital D of v mu u mu, capital D of a scalar field is same as df. So this is same as d of v mu u mu. Okay. All right. D of v mu e mu, because D obeys Leibniz rule, this is same as d of v mu u mu plus v mu d of u mu. Because d differential is a derivative operation and it must satisfy the Leibniz rule, that we know. But so would capital D. After all, capital D is also a differential and it must also satisfy Leibniz rule. There's an assumption, but it's a valid assumption. So under the assumption that capital D also satisfies the Leibniz rule, this must also be capital D of v mu u mu plus v mu capital D of u mu. Okay, so let's put them all together. You will find, I mean, all those people who have been trained in mathematics, they know very well. Mathematics will always give you the correct result, provided you write things in a neat fashion, follow logic without making mistake. Then whatever you end up with will never be incorrect. Okay. That's why the standard mathematics going from one to another, a computer or AI can easily do it because it's just mechanical, standard. But whether AI can develop the rule of how to parallel transport, that is a separate thing, because here getting this expression was not a logical thing, it's a jump of imagination. So whether jump of imagination or thinking out of box, whether AI system, Prakash sent recently the mail how AI has solved many of the puzzles. So eventually AI will do it, perhaps. But that's the reason why, we later on should not become slaves to AI. We must have our own mathematical prowess, knowing that human beings are the only people who can do mathematical thinking. Right. So now let's write down everything systematically so that, so capital D v mu u mu, that I know what it is. It is this. So we know that this is v mu semicolon alpha dx alpha. This is my capital V mu and E mu, U mu. plus V mu d of u mu this is equal to ordinary differential dv mu u mu, which is nothing but del v mu by del x alpha dx alpha u mu plus v mu ordinary differential is del u mu by del x alpha dx alpha. Okay. Now let's expand this. What was this? This was this object was del v mu by del x alpha dx alpha plus Christoffel symbol gamma mu beta alpha v beta dx alpha okay. Now all the magical things will happen. Note that del v mu del x alpha dx alpha u mu, this is acts here, so I can just cancel this term. What is remaining is that v mu d u mu, this term is remaining, which is plus gamma mu beta alpha v beta u mu dx alpha is equal to v mu I hope I have not made index errors, because in tensor calculus, because there are too many indices you are handling with, so it's very easy to make calculational errors. So let's take a pause and see whether any mistake has been committed. V mu d mu gamma mu beta alpha v beta dx v beta u mu dx alpha v mu del u del x. Yeah, it looks okay. Now you see, I would like to take v mu term common. There's a reason I want to take, and v mu is here, but here it is v beta. So is there a problem? No, there's no problem. After all, mu is anyway being summed over, beta is also being summed over. So all we have to do is rename them. So instead of calling this as mu, I can call it beta, and instead of calling this as beta, I'll call it mu. And this I'll call it beta. You'll soon realize why I did this. Then you see, I'll take that term v mu, whatever is there in the right hand side, to the left hand side, and take v mu common. Then I'll get the result. So v mu, v mu, v mu appears everywhere. I'll take v mu common, and I get the result. So I have taken this to this side. Because I have taken it to this side, so I'll overall take a minus sign, because that has been taken this side, so minus. And this was plus, because I have taken overall minus, so I'll put a minus sign. So I'll get okay. All right. As I said, as we have been saying, anytime you think there's a problem, just stop me and ask. Okay. Okay. So what have we achieved? Let's take a pause and ask ourselves what we have achieved is we took an arbitrary contravariant vector field u mu and we wanted to know what is its actual differential. Because we know what is the differential, actual differential of a contravariant vector field, we know the actual differential of a scalar field, we used all the machineries and finally we ended up in this equation where we have the capital, that means the actual differential of the contravariant vector field and all these expressions, that whole thing is equal to 0. So you'll say, so what? Now we are talking about a vector relation, and in vector relation, if you have an equation which is true for an arbitrary vector field, this is telling me for an arbitrary v mu, this equation is correct. If for an arbitrary vector field v mu, this equation is correct, then whatever is there in this square bracket must be 0. Because this v mu is not a specific vector field, it is an arbitrary vector field. If this equation has to be true for any arbitrary v mu, then whatever is there in this square bracket must be identically 0. Okay? Yeah, you have a question, Snehil? Yeah. So this immediately implies the fact that v mu is arbitrary, we have the result that actual differential of u mu is indeed equal to del u mu by del x alpha minus gamma beta mu alpha u beta. Dx alpha. And therefore, this is indeed the covariant derivative of u mu, so I can write it u mu semicolon alpha dx alpha. So from now on, I'll adopt the notation, the covariant derivative will be, covariant derivative with respect to x alpha will be semicolon alpha. Just like ordinary partial derivative with respect to x alpha, I will denote it as comma. This is the Landau-Lifshitz notation. I'll stick to the Landau-Lifshitz notation.
I have a, maybe I'm wrong, but in the first expression while calculating this covariant derivative v mu alpha dx alpha u mu plus v mu derivative capital D of um, which can also be expanded. In that case, then these terms will be, I mean, why haven't you done that, like expanded the capital D in the case of the second term on the left hand side of the
Second term meaning which term?
the first step?
Here.
Yeah.
But I don't know what is capital D of u mu, no? I don't know. That's what I am trying to obtain. I have no idea what is capital D of covariant, I don't know. And that's what we finally end up getting at.
Why can't we use the same sort of
No, see, we have to stick to, I could have started with u mu and then asked, because I must not invent another Christopher symbol, no? See, it's a very good point. So what Prakash is asking, why don't we again start with the first principle for a covariant vector field? I can again do that. Del of v mu will be proportional to, del of u mu will be proportional to u mu dx alpha. But proportionality, what will be proportionality? Will I use a different symbol or the same symbol? I better use the same symbol, na? But then, what form will it come? Will it be minus? Will it be plus? I have no idea. So therefore, mathematicians say that since I have done it already for contravariant, I know for the ordinary scalar, might as well use it. Otherwise, it will be two different crystallizable field. But that's an important thing. No, I never thought about this argument. Suppose, this is a very important point. Someone should, it might result to something very interesting. Suppose I do independently and I introduce two crystallizable symbols. Okay? I introduce absolutely two different crystallizable symbols, one for contravariant, one for covariant. And yet, by some magical mean, I obtain that capital D of scalar field is ordinary differential of scalar field. By some, if you directly try to do it, you'll find that you'll again get back the same result. But can we think of a different mathematical scheme where you have two different crystallizable symbols, yet arrive at capital D of f is small d of f by some suitable assumption, and can we have a different tensor calculus? That should be actually interesting. Then you'll have two parallel Riemann curvature tensor. That can be a very, very nice extension to normal general relativity if it can be done cleverly. Yeah?
We define covariant vector at first, let's say, or contravariant, then the other one should be a derived quantity, right? As in how they can be independently.
No, we are now trying to think of a new mathematical scheme. No, that's the standard thing. The standard thing is, if you don't want to introduce a new proportionality constant, here crystallizable symbol was used as a proportionality thing. We say that, look, that is the thing that Christoffel, Riemann, Gauss, they did. But supposing we want to do something new, we say that this is for the contravariant vector field. I will again use for the covariant vector field, I will ab initio do the similar reasoning, introduce another gamma bar thing, but I must satisfy certain thing that capital D of f, and also say, let's say, that capital D of f is not equal to small d of f. But you have to give suitable mathematical reasoning. Can you obtain a alternate formulation of tensor calculus and say that a alternate formulation of general relativity can solve some of the problems which normal general relativity is not able to solve? That will be an interesting problem actually.
But the space-time metric is still same, right?
What?
If the space-time metric,
No, at the moment yet metric has not come. That's a additional thing. You see, I don't know how gamma is related to metric, and so far I have not even talked about metric.
No,
Yeah, we'll come to it. Manifold
is the same, then how can we say capital D of f is not equal to small?
No, but you might say that, look, how we are using again physical reasoning that a real function at a given point is a real number. The same function at a different point is another real number. And differential must be real number minus real number. But that's a, supposing, for example, for quantum theory, if it was not a pure real number, it was an operator, this will not be true. And perhaps, there will be a fan, e raised to a phi. So, supposing I want to say that I want to, in the view that unifying general relativity with quantum mechanics is creating a lot of problem. That's one of the big problem of quantum gravity. So, can this approach give us a new version? So, one should actually do it.
Even if you take a new gamma connection over there,
Yeah.
would it be have to follow the same procedure?
We'll follow the same procedure.
Even if you, let's say you define it that way, and
Huh.
you define, for covariance you define different connections, and contravariant you define different connections. You would have to ensure that the D of scalar product.
That's what I'm saying, that how strong is that requirement?
If you do the same calculation, take two different connections, you will end up, the end of the equation will end up saying that the
Provided capital D of f is same as small d of f, provided that. But that's what we are discussing. How stringent is the requirement that capital D of f should be small d of f?
I thought that just followed from differential geometry. Like once you have a manifold,
No.
you have defined the points in that manifold.
Yeah, but can we do a alternate thinking and without disturbing many other tenets of geometry, whether that's what is creative. creativity, right? Without disturbing.
This year is breaking something
Yeah,
else if we
yeah.
say that they are not equal.
Exactly. So one should think about it.
So this is the usual procedure for this is the normal tensor calculus that we.
Yeah, what I am following is normal tensor. But after Prakash's question, we were thinking of forming a alternate tensor calculus.
Can this same be derived or explained on the basis of the differential geometry?
Yeah, all these things can be done from differential geometry. So differential geometry and tensor calculus, the differential geometry was created by Elie Cartan, except for certain things like torsion, etc. They give you the same result of tensor calculus.
So thinking of parallel transport, how can it be imagined in differential geometry?
It is done through connection. You have to define a connection. So that's where fiber bundle approach comes. So basically, tangent space is a fiber bundle actually. I mean, at different point you have different tangent plane. So how do you go from one vector on this tangent plane to another vector in another tangent plane? I don't know whether TP talked about fibers. So fibers, if you have a circle and things sticking as fiber, how do you go from one point of the fiber is not there in the base manifold to another point on another fiber at a different base point? And then you have developed the notion of connection, the gauge connection. So it's the same thing which is done, okay, in the perspective of differential geometry. I'll get back the same result, except when torsion is there, the two results. I'm talking about a case, I'll talk about when I'm assuming torsion is 0. We'll do all that. Yeah, so Prakash, I think one should pursue it. Perhaps you'll not get anything new, but nevertheless, that's what creativity is all about. One should pursue things, see how much we can develop a new formalism.
So, but I think she had a right point by saying that for one matrix we were not seeing
I'll come to that. As far as the present point is concerned, I have not even related the crystal symbol with metric. When can they be related? That's what now I am coming to. That's precisely the point. The crystal symbol can be obtained out of the metric tensor through derivatives under a given assumption. That assumption is nothing very holy. What is that assumption? We'll discuss that now. Okay, now I'll erase that part. Yeah, I mean, this is an advanced course. Such questions are very important. Yeah, because these are something even AI, I'm sure, will not be able to discuss. Now we come to metric tensor. So far, I have only yesterday talked about in the differential geometry what is a metric. It's an object which takes two vectors and produces a real number. It's a basically G mu nu, differential form dx mu, tensor product, differential form dx nu. But now that we have, so for us, in differential geometry, this metric by definition is G mu nu at x, differential form dx mu, tensor product dx nu. Because we are now going to only talk about components, I will now only talk about the components G mu nu x. So in tensor calculus, we will deal with only G mu nu x. All right. So, metric tensor. Metric tensor tells me, by the way, now I will say something you should not get confused notationally. This dx mu is not a differential one form. That's why differential one form was d tilde. Okay, so that's very important. So in differential geometry, therefore they never use the dx mu. Now, what is the? Okay, before that I have to say something. Yeah, that's also important. That's also important because without that, yeah, so, okay. So, fine. So, we talked about contravariant vectors, covariant vectors and so on. In the tensor calculus approach, how do contravariant vectors transform under coordinate transformation? That we know. V mu, when you go from a coordinate x to x prime, is such that V prime mu, I'm not going to elaborate on it, I'm assuming that you know what V prime of x mu, x prime is. Contravariant vector field transforms like, this is how contravariant vector fields transform, and covariant vector fields transform as under coordinate transformation. Okay. This we know. I mean, I'm sure you would have studied all that. In standard tensor calculus, contravariant vector fields and covariant vector fields are those which transform like that. Okay? All right? This is something is well known. I'm not going to discuss more on that. Just for the completeness sake, I have written it down. Okay? Now, it's trivial to immediately realize not the one differential notation problem, dx mu is a contravariant vector, not d tilde. So, that's the reason when you first learn tensor calculus and you go to differential geometry, the notation will make you highly confused. Okay? So, dx mu is not d tilde. D tilde x mu is a one form. Dx mu is a contravariant vector. Why? Because dx mu. Why? Because dx prime mu by definition is del x prime mu del x alpha dx alpha. So it transforms like a contravariant vector. On the other hand, del by del x mu transforms like a covariant vector, while in differential geometry del by del is a vector field. So these are some of the confusing things. I mean, when I first started learning differential geometry, the tensor calculus things were completely opposite to differential geometry. So you must be very careful. This is not a one form, it is dx mu. This is not a vector, it is derivative with respect to coordinates, okay? This transforms like a covariant vector because del by del x prime mu by definition with partial, what is chain rule of partial derivative. This is okay. Okay. So therefore, in the tensor, now I am completely doing tensor calculus. I am not doing differential geometry. So dx mu is not a one form. Del by del x mu is not a basis vector of vector field. Okay. So that you must keep in mind. All right. So now that we have g mu nu x, dx mu is a contravariant vector. Dx nu is a contravariant vector. If mu nu is being summed over, this is a scalar quantity that we know for tensor calculus. This is a scalar, and this object is invariant under general coordinate transformation, and it's called the proper distance. So ds square is the proper distance between two events. So we have two events, x mu then a metric is that quantity that gives you the proper distance, square of the proper distance. Okay. All right. Now, so far it's all mathematics. Now we come to physics. By physics, I will say that yes, in arbitrary coordinate system, mathematicians tell me the proper distance between two events or 2 points having curvilinear coordinates, one having curvilinear coordinate x mu, the other having curvilinear coordinate x mu plus dx mu. Mathematicians tell me if you are given a metric tensor G mu, then the proper distance meaning it doesn't depend upon which coordinate system you have chosen, then the proper distance is given by this. Now you say that, well, I am a physicist. I want to know what does it mean in real world. Einstein, go back to my first lecture. What did I say? I said that one of the greatest, Einstein himself said, that was the greatest, that was the day that gave him the greatest happiness when he realized that no matter what kind of gravitational field you are in, whether gravitational field is uniform, non-uniform, time dependent, static, doesn't matter. In any kind of a gravitational field, I can always choose a frame of reference which is sufficiently small in extent, sufficiently small in duration, such that in this reference frame, the gravity, the gravitational field, gravity simply disappears. And physically, what is that? Because Einstein was a man of physical intuition, physical feeling. In some book, he says that I understand force by how much strain I feel when I press something. He was that kind of a person. So, what is that frame physically? The frame physically is that a freely falling frame. But what is the frame mathematically? If it is free of gravity, and he has already said free of gravity, all relativity, special relativity rules apply, and therefore his teacher had formulated Einstein's special relativity in terms of Minkowski metric, etc. So Einstein said that, okay, mathematicians tell me this, in the local inertial frame, if I view these two events, this is an arbitrary coordinate system, but these two events can be viewed also in a frame of reference which is freely falling. This is called local inertial frame. Namely freely falling frame. These two events in a freely falling frame, I will use Minkowskian coordinate system xi mu. So instead of using curvilinear coordinate system, I will use Minkowskian coordinate system xi mu, xi alpha, let's call it xi alpha d xi alpha. And in this frame, the same ds square is equal, will be eta alpha beta d xi alpha d xi beta. In other words, Einstein is saying that no matter what kind of a gravitational system you have, what kind of curvilinear coordinate system you choose, the invariant distance, proper distance between two events, one event happening at x mu, so these are two events, event E1, event E2. In the curvilinear coordinate system, the proper distance will be given by this, but the same distance in the local inertial frame will be given by this. They are all equal. That means this is same as G mu nu okay.
This is only for local inertial frame where G mu is eta alpha.
So, good question. So, what one is saying is that in a local inertial frame, you can always choose for the space a Cartesian coordinate system and a set of good clocks, such that the proper distance from special relativity is given by this, and this is invariant under Lorentz transformation. It turns out that this local inertial frame is not unique. The freely falling frame, which is your local inertial, is not unique. Why? Because my friend who is also freely falling, he could rotate his coordinate system. My z, x, y is this, but my friend who is also freely falling and freely falling with me at the same point, he might choose a coordinate system which is rotated with respect to me. Not only rotated, my friend and I, we are freely falling at the same point. He might be moving uniformly with respect to me. That means what? The whole class of local inertial frame at the same point is infinite. And this is going to be important when I talk about the tetrad formalism. So, there is no unique local inertial frame. They can be rotated with respect to each other. And yet, and of course, xi alpha, therefore, there is a whole class of xi alpha which are related by Lorentz transformation. And a person who says that, no, I don't want to fall freely, I will therefore have my own coordinate system x mu's, so that the event is g mu nu dx mu dx. Okay. All right. In other words, there is a class of coordinate transformation from x mu system to xi alpha, so that this is after all a covariant second rank tensor. You know what is the transformation properties of, because I have done it for this, I might write it down as well. Any covariant second rank tensor b mu nu under coordinate transformation, by definition, transform to b prime mu nu. By definition, it is nothing but del x alpha by del x prime mu, del x beta by del x prime nu multiplied by b alpha beta. This is a transformation property for a second rank covariant. So therefore, g mu nu will go to g prime mu nu, satisfying this, and you can always therefore choose coordinate system locally, so that around a event point, your arbitrary g mu nu around that point will be eta mu nu. In fact, we had given a tutorial, a preamble problem right in the beginning, that how to choose the local inertial, how to go into freely falling frame. Yeah? Okay. Now I'll go to that part of the board. We know how to, by the way, I'm not going to tell you how to get the covariant derivatives of arbitrary rank tensor. It's the same approach. And we have done it already. So as a tutorial problem by yourself, you can find out what is the covariant derivative of a tensor of the form nu alpha beta. Find out what is the covariant derivative of this. Same process. Where any arbitrary tensor can be written as a product, a product of, suitable product of contravariant vectors and covariant vectors. You find out the covariant derivative and it should match with that.
Is it just a matter of convenience and convention that we stick to a covariant derivative instead of also defining contravariant derivative or something?
Oh, there's a nomenclature. So I think the reason why you call it covariant derivative is the index lies below.
No, so we don't use a contravariant derivative.
No,
Just because we just stick to one convention.
Yeah, because covariant derivative, like partial derivative, the index is below. Anything index below, you call it covariant. Index upwards, you call it contravariant. That's.
You can take a contravariant derivative and do this.
You can raise the index, no?
It's only reason.
Raising is done by metric. Okay. So, one purpose of the metric is to produce a scalar quantity giving two vectors. So, because dx mu, dx nu, they were contravariant vectors, I produce the proper distance. You take any two contravariant vectors, g mu nu can be used to get a scalar quantity. That's obvious. Now I'll give you another property of the metric. Okay, but before that I must complete one. This tells me that g mu nu is it describes the geometry of the space-time. Now this is very important. What is geometry? We have been reading geometry from our school days, but what is geometry? Geometry is a field of mathematics that tells me how to find out distance between 2 points, and if you have two vectors, how to find angle between them. That is the subject of geometry, and metric precisely helps me doing that. It gives me distances, and if you have two vectors, if you know the distance between two vectors, you can also compute the angle and so on. So knowing metric g mu nu, I can get the angle between two vectors, I can find distance of a vector, magnitude of a vector, but the distance is that fact that it's not positive definite, because we are talking about c square. The metric is not plus 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 plus. It's either you say minus plus 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 or plus minus minus minus. Because of this, it's not a positive definite distance. Because in real world, that's what Einstein and Minkowski showed. That was a big surprise. We don't live in a Riemannian geometry where you have a positive definite metric. I'll come to that because that gives you the causality. All the causal horizon, etc., is because of all that. Yeah, so, yeah, what was I saying? Yeah, geometry. So, geometry by definition is that branch of mathematics which tells me how to compute distances, how to compute angle, and g mu precisely does it. That's the reason g mu characterizes the geometry of the space-time. And because in the local inertial frame, g mu becomes eta alpha beta, and eta alpha beta in the matrix form, I can choose this convention, minus 1, minus 1, minus 1, 0 in the off-diagonal. Or in other words, I mean, you don't have to write it as a matrix, but all what one means is eta 0, 0 is plus 1, and eta ij is Kronecker delta minus delta ij. That's all in this convention. Okay. I can write it as a matrix because any two component object can be treated as a matrix. That means, again, now I have to make it clarified because you may get the impression that gauge theory of fundamental forces is also geometry. But you have to qualify, what does it mean? It's nothing to do with space-time geometry. Yes, gauge theory, just like we have got a covariant derivative, and covariant derivative tells me how to have a derivative of a vector field which transforms like a tensor. Covariant derivative of a gauge field tells me if something transforms under a group, the covariant derivative must also transform the similar way like a group. But this has nothing to do with space-time geometry. So whenever someone says that gauge theory is a geometrical formulation of other interaction, you have to remember it's a geometrical form in the sense of in the internal space. It is nothing to do with space-time geometry. The only interaction that can be formulated in a space-time geometric approach is gravity. And the reason is gravity is universal. Everything gravitates like geometry. Space-time geometry will tell everything to move in the same way, just like gravity. But gauge theory interaction doesn't tell you all objects should have the same thing. Weak interactions will tell you those which has weak charges will interact weakly. Electromagnetic forces will tell you only those which have charges, electric charges, will be affected. But neutral particles don't get affected by electromagnetic forces. So there's no reason why electromagnetic forces should come out of space-time geometry. That would be completely wrong. Right. So having clarified the issue, because sometimes people don't realize what was the astounding thing that Einstein achieved, that the gravity, the universal gravity, is equivalent to the geometry of space-time. That's what Einstein. So here let us pause and say what did special relativity do and what did general relativity do. Special relativity unified two things. Unified meaning brought space and time in the same framework. Time became the fourth component, but there's a difference. It's really not a fourth dimension. I mean, because in signature is different between time and space. Time and space came together due to special relativity. What else came together? Energy and momentum came together. Good. What else? Energy and mass came together. Energy and momentum, they are components of a 4-vector p mu. And energy is same as mc square. So energy and momentum got unified. Energy and mass got unified, and energy momentum are described by the same 4-vector. That was the achievement of special relativity. General relativity did what? What achievement? It says gravity is equivalent to the geometry of the space-time, and what determines the geometry of the space-time is the energy momentum of matter. So these are magnificent achievements which got overshadowed by later particle physics development. Because all kinds of new interactions came up, new particles came up. So all these achievements got somewhat overshadowed. But there is always important to highlight the revolution, the so-called space-time revolution that happened between 1905 and 1916. Right. Yeah. So metric, the G mu nu is the hallmark of space-time geometry. What else can we do with the metric? One thing we can do is G mu nu is at our disposal. Given any contravariant vector field V mu of x, you ask, what is G mu nu V nu of x? How does it transform? It's obvious. If this is a contravariant vector, this will transform as covariant vector. Obvious. So therefore, G mu nu is cardinal, because G mu nu is, there is only one G mu nu which describes the geometry. So therefore, why should I call it something else? I might call it V mu itself. So for every contravariant vector V mu of x, there is a one-to-one correspondence with a covariant vector field. Okay.
What is that term, cardinality?
No, I just use cardinal means important. So G mu nu is not any arbitrary covariant tensor, second rank tensor. It's a very special covariant tensor field, namely it is a metric. That's why I'm saying I use the word cardinal.
This cardinality?
No, that's separate. The cardinality of a set, that is if you have an infinite set, like the set of integers or set of natural numbers is infinite. 1, 2, 3, 4, you can go up to any number. Set of real numbers is also infinite, but this infinity is same as this infinity. That people like Cantor, etc., and they showed that the set of real numbers is much bigger than set of integers, and it has a cardinality greater than. Anyway, I don't want to go into that notion of cardinality. Right. So what did I demonstrate? I said that for every contravariant vector field, there is a covariant vector field, because I can contract, remember, whenever two indices repeat, it is being summed over. It is going from 0 to. So given a metric, so far I have seen it has served me two purposes. If I have a metric, I can find out the geometric distance between two events, invariant distance, ds squared, g mu nu dx mu dx nu. Another purpose that metric serves is, given any contravariant vector field, I can get its corresponding covariant vector field by contracting with the metric tensor. Then someone will say, can we do the reverse? Given any covariant vector field, can we get the contravariant vector field? You can do it provided your metric tensor as a matrix is invertible. Okay. So, if G mu nu as a matrix with any two component object can be written down as a matrix, square matrix, is non-singular. By non-singular, it means it can be inverted. So that its matrix inverse exists then if U alpha is a covariant tensor, covariant vector, G mu nu of U nu x is a contravariant vector, obvious. So there is really an equivalence relation. Of course, we have to be mathematically very clear only for those space-time for which G mu nu as a matrix is non-singular. That means its inverse exists. Inverse exists meaning what? If I am representing G mu nu as its matrix inverse by matrix multiplication, that means G mu alpha, G alpha nu, matrix must be Kronecker delta. Yeah.
I have a basic question. So this is clear what is covariant and contravariant vector. Why are we obsessed about like this transforms like covariant, this transforms like this? It's all about like how we are summing, right?
Huh? No. Covariant vectors and contravariant vectors, they are defined how they transform. For example, look at a contravariant vector. When you go from one coordinate system to another coordinate system, its transformation rule is this. Well, a covariant vector's transformation rule is very different. So they are different. They are different. Look at this.
Yeah, I understand that. Like you can understand one as a row vector and column vector in basic way. Or
No. They cannot be understood that way.
They cannot be.
That's why we did differential geometry. Covariant vector components are the components of a one form, and one forms are not vectors, while contravariant vector components are the components of a vector. They are two different objects altogether. But what we have found is, if you have a metric, there is a mapping from one form to vectors. So having a metric achieves two things: a notion of distance, which is essential for talking about it as a geometry, and a mapping from vectors to one forms. We are that for every contravariant vector field, I have a covariant vector field, and vice versa. So metric has an elaborate role. That's why I use the word cardinal. Metric is something very cardinal quantity, it's very important.
And the property that metric is symmetric, does physically means there is no preferred code direction?
No. That's a good question. Even if I add an antisymmetric term to the metric, there are theories of gravity, alternate theories of gravity, where they say, no, my metric is not symmetric. But this term will still be ds squared, where dx nu is symmetric. Even if there is an antisymmetric term, that antisymmetric term, when you multiply by dx nu and sum it over, 0. Because it's a trivial proof, and those who like mathematical exercises, you can show that if you have a antisymmetric tensor, that means a mu nu is minus a nu mu, and if you have a symmetric tensor, b mu nu, which is b mu nu equal to b nu mu, is identically 0. It can be proved very easily.
Does that say something physically?
Physical meaning?
In real world, how does that mean? Something to do with order of coordinates, something?
No, first of all, such a theory will not satisfy equivalence principle, because in equivalence principle demands that G mu nu must go to eta alpha beta in a local inertial coordinate system. Eta alpha beta is manifestly symmetric. So a theory in which metric is not symmetric in a local inertial frame will not go to eta alpha beta. There will be an antisymmetric. So it will violate equivalence principle.
So the notion of distance will also be different.
No, notion of distance will not be affected, because the antisymmetric part, when you contract with dx nu will be 0. It will not affect.
So we cannot calculate the ds square using that.
The other part will not affect the calculation of the proper distance between two events.
So is there any physical meaning to covariant and contravariant? So like any physical, like why the electromagnetic tensor always is given the form of a covariant form?
No, but physical measurement, see, physical meaning, so at the advanced level, when we ask what is the physical significance of this, what you mean is how does it affect in our real measurement. So if you take F mu nu as the field tensor, electromagnetic field tensor, is there a physical significance of being F mu nu being mu nu downstairs? The answer is no. I can use in flat space time, I can use the Minkowski metric to raise the indices. That's all. I can have F mu nu upstairs using the Minkowski metric, because upstairs and downstairs, if you have a metric, there is nothing, they are same. But the physical significance of F mu nu is that F0i components, what do F0i components represent?
Like that's of 0?
No. So what are electric field and what are magnetic field? F0i's correspond to electric field and Fij's correspond to magnetic field. And electric and magnetic field, when you do experiments, their physical effects are different. A static charge particle will be only acted upon by electric field, not by magnetic field, while a moving charge particle is acted upon both by electric field and magnetic field. So the physical significance of F0i and Fij are different. But coming to Snell's thing yesterday, that when you reformulate, so he asked a different question, but now that you have done the tutorials, Bhashwati has done it, that how to write down Maxwell's equation in terms of differential geometric thing, because there the vector potential A mu is a one form. So A, which is A mu dx mu, and the field tensor F mu nu is a two form, the Faraday two form F, which is F mu nu dx mu vec dx nu. But now vector, the one form vector potential, two form field strength no matter which coordinate system you choose, they are the same, they don't change. Okay, so in differential geometry language, these have a status of things which do not depend upon your coordinate system. However, if you want to make a correspondence with measurement, you have to go to a frame of reference, and therefore you have to come down to components, because measurement, an observer does the measurement, an observer doing the measurement has to be anchored with some coordinate system. Yeah, I will, although it is 1 o'clock, I'll still take a little bit of time to make another very physical correspondence that Anuj has already talked about in his tutorial problem, but I want to do a reinforcement, because sometimes we learn better when the same idea is reinforced using a alternate mechanism.
I have a sorry, I have one doubt. Like when you mentioned about vector contravariant when we are transformation from one form to vectors, but
I didn't transform a one form to a vector as yet. In the differential geometry, one form and vectors were two separate beasts. One form acted on a vector to produce a number.
are vectors
Here what I showed is a contravariant vector field is uniquely related to a covariant vector field using G mu nu. In the tensor calculus, for every contravariant vector field, I have a covariant vector field, and vice versa if you have G mu nu upstairs also.
Always invertible.
Not always. There are cases, but they are of course theoretical cases. In real life,
What is the physical cases when it is not invertible?
I don't know of any physical concrete problem in which metric is non-invertible. On the other hand, there are coordinate system for a physically realized situation. Some metric coefficient can be 0. Black holes. We'll talk about black holes. But it is only a coordinate singularity. But I don't know of a concrete example that talks about actual physical systems for which metric is non-invertible. But Ashtekar, when Ashtekar gave his new variables, one of the prime aim was that can we still do general relativity when metric is non-invertible. One of his positive thing that he showed using new variables, he had given a set of lectures right here in Pune University when he had just developed, those days they were called Ashtekar variables, and which led finally to the loop quantum gravity over the years. His one of the primary result, he was very happy that his theory works even when the metric is non-invertible. So these are theoretical consideration. Yeah, one thing, yeah, so which is to do with actual physics, which actual experimental tests of gravity. Now I go to free particle again. Yesterday, towards the end, I talked about free particle, what was his action, but that was a free particle in flat space-time. Now, I say that, okay, in flat space-time, the action of a free particle is its rest mass, speed of light, and integral ds, which is eta mu nu dx nu dx nu, or d. For Minkowskian coordinate system, I am using the notation xi mu. Now Einstein will tell me that, okay, I have already made a correspondence between curvilinear coordinate system, gravity, and special relativity. Therefore, when there is gravity, all we have to do is the same particle, its action is minus mc. After all, this is invariant under curvilinear coordinate system. Okay. Now you will say, okay, fine. And yes, the metric tensor, according to Einstein, is about space-time geometry, but is also about gravity, because Einstein assures us that gravity is nothing but the manifestation of the space-time geometry. So everything about gravity is encoded in g mu of x. Then you say that, okay, can I consider a case where I am far away from gravity, the gravity is very weak. So let me ask, what happens for a case when a slowly moving particle, the case, I am talking about one case, a slowly moving particle far, far away. This sounds like Star Wars preamble. Far, far away from a galaxy. Anyway, far, far away from gravitating sources. This is a case I am interested in. But if it's too far away, I should be able to set up coordinate system which are very much like Minkowski's coordinate system. But yes, gravity is not zero. There are matter present, right? You can't wish away the matter. No matter where you go, no matter, I mean, the English matter and the physical matter are coming in the language. So no matter where you go, you will always see stars and galaxies. There will be actual matter. So therefore, you can't set up a coordinate system where everywhere you get a metric which is eta mu nu. But what you will find is you can go far away where your g mu nu x is eta mu nu plus a very tiny perturbation h mu nu of x. Okay, where tiny perturbation meaning what? Modulus of h mu nu of x must be much small compared to eta mu nu. But eta mu nu, what is the maximum value of eta mu nu? 1. So therefore h mu nu of x must be much, much less compared to 1. What? Yeah, I have gone into linearized gravity, correct. Because if you are in very weak field, so weak that the perturbation is much small compared to the Minkowski metric. So when you go to real physics, what is the difference between mathematics and physics? Mathematics doesn't do approximation. When you talk about real physics, there is no branch of physics where you will not do approximation. No branch of physics. You tell me that a block sliding along frictionless surface. There is no frictionless surface. All you can say is you approximate that the friction is so tiny that loss of energy and momentum is very small. So real physical world, you have to make approximations. So you are making approximations.
Why is the slowly part important?
What?
Why is the slow part important?
I'll come to that. Because Newtonian gravity, wherever we know Newtonian gravity, all the Newtonian gravity validity is for particles moving with speed much small compared to the speed of light. Our Earth moves around Sun at what velocity? These are very important numbers. Earth is going around Sun with respect to Sun. What velocity is it? About 20 kilometers per second. Sun is going around the center of Milky Way at what velocity? 220 kilometers per second. These are tiny compared to speed of light.
But already we are in sort of special relativity regime, right? Eta.
No, eta mu is a metric. Special relativity is always valid, but our velocities, the velocities that confirm Newtonian gravity. Newtonian gravity has been experimentally shown to be very good. All our rocket exploration, satellite exploration doesn't need general relativity. It uses Newtonian gravity because the velocities are much small compared to the speed of light. So now you will say, very good, I will use the fact that the particles move very slowly, and I will also use the fact the perturbation to the Minkowski metric is extremely tiny. Let's find out what happens here. By the way, m is the rest mass and not the moving mass, although strictly speaking I should use m0 for the rest mass. By the way, okay, so let me go stepwise. I mean, I must not. So, eta mu dx mu, that I have considered yesterday. So, this part, square root of no, is a test particle. So we are talking about a slowly moving particle, which is a test particle. Just like when we do electrodynamics, we say that an object has produced electric field and I want to study the motion of a test particle. Then you say test particle is not changing the electric field and magnetic field, and its trajectory will be given by Lorentz force. So m into dp by dt will be charge into E plus V by C cross B. But this is strictly speaking, the test particle itself is not perturbing the external electric field and magnetic field. So I am talking about a test particle which is, its mass and energy are so small that it has not by itself perturbed the ambient geometry appreciably.
But if its self-gravity is compared to h, it can...
Yeah, so I can't use a black hole as a test particle. So I can't use this, that a black hole is moving slowly. That will be completely wrong. Right. This, yesterday I talked about, this is nothing but minus mc c square dt square minus v square, okay, this part, plus h00 c square dt square. Remember dx0 dx, I should have mentioned that dx0 is simply c dt and dxi are the spatial components, dx, dy, dz in Minkowski coordinate system. Again, I is being summed over, but I, in my convention, I goes from 1 to 3. They are spatial, while mu goes from 0, 1 to 3. I have split it up into time, dt square. Time, space. Why is this factor 2 there in H0i? Huh? It is a symmetric metric, so there will be a term h0i c dt dxi, there will be a term hi0 dxi c dt, which is the same. That's why a factor of 2. Again, stop me, because if it is not familiar, if you are encountering for the first time, stop me if there is a doubt. Oh, I made a mistake. No one pointed out mistake. This is not v square. This is dr dot dr. Therefore, I never trust my memory. Whenever I make a mistake. It's better to go follow the mathematics. If you follow the mathematics, you will not make a mistake. Now, as usual, what I'll do, I'll take c square dt square outside the square root, so that I get minus mc. Because I am taking c square dt square, it will be c dt, so there will be c square integral dt 1 minus, and c square dt square has come out, dr by dt is velocity, so I get v square by c square, and then here I get plus h00, c square dt square I have taken out, and then plus 2 h0i, because c square dt square has come out, c vi component, because dxi by dt is simply the ith component of the velocity. Dxi by dt is vi plus c square dt square has come out, so hij by c square vi vj, velocities vi vj, square root, there is a square root to the power half. Okay. Now, as I am slowly particle far away. Far away mean the gravitational effects h00, h0i are too tiny. Slowly moving means vi by c is extremely tiny. So therefore, compared to 1, where is the 1 here? Compared to 1, these are very tiny, and therefore I can expand it. Taylor expansion means my action to first orders action is minus mc square integral dt square root, I have made a Taylor expansion, is 1 minus v square by 2c square plus half h00, and these are quadratic. h0 is tiny, v is tiny, v square by c square, they are very tiny, h is very tiny. I can neglect it, because not only v is tiny, h is also tiny. So I will retain only up to this. That's why it's approximation. You got my logic? Not only slowly moving, vi by c is small, h itself is small. So I am neglecting, although I should have retained this, because there is something to do with, we are talking, I think Vishnu and I were talking, or someone, these are the gravitomagnetic field. There is a gravitostatic field, gravitomagnetic field. I think Debabrata and I we were talking today morning. So these lead to gravitomagnetic field. But let's not bother about gravitomagnetic field. I'll drop this term. So this is the thing. Now expand it out, take it out and all that. Then you get the yesterday's. So I'll get a term. This is from T1. Action is always from a trajectory from T1 to T2. So I get mc square T2 minus T1. This is a pure constant. It will not affect the dynamics. This will give me the kinetic energy, half mv square T1 to T2. And this will give me, minus. Minus has become plus. Okay, this is a plus. But there is a minus here. This minus half. Okay? All right? So, what have we achieved? We say that for a slowly moving particle, in situations when the gravity is extremely tiny, the action is given by this quantity. That means Lagrangian is half mv kinetic energy minus a potential energy. But in gravitational field, if you write the Lagrangian for a particle moving in gravitational field, what is the Lagrangian? Lagrangian is T minus V. T is of course kinetic energy for a gravitational field. And what will you get? Oh, by the way, M is also here, right? I have made some mistake. Minus mc square, that goes, but minus mc square, there's a minus mc square. Yeah, so if you didn't know about all this and someone told you a particle is moving, Newtonian particle is moving in a gravitational potential, and say that you write down the Lagrangian and find out the equation of motion, your Lagrangian would be simply what? If the potential, gravitational potential is phi, then it will be m phi. Okay? This would be your Lagrangian and m phi, and you will do all. So therefore, you immediately see that this object must be identified with m phi, or the Newtonian potential is to be identified with c squared by 2, 0, 0 component of the perturbation. In other words, the 0, 0 component of the perturbation is 2 phi Newtonian potential. Phi is the Newtonian potential divided by c squared. And hence, you can find out the gravitational redshift as Anuj did. You can find out gravitational the fact that clocks slow down in strong gravity can be inferred from this. You can do the parallel precision using this. You can do bending of light. So all can be done using this correspondence that the 0, 0 component of the metric perturbation is simply twice Newtonian gravitational potential divided by c squared. Okay. No, but you can still talk about how much correction you have. Sun, see, bending of light experiment was performed. I mean, the team that was led by Eddington, they did about bending of light for a light beam grazing past sun. Sun's gravitational field is very weak. So what do you mean by weak gravitational field? So if someone tells me, when do I, if I want to use Newtonian gravity instead of general relativity, when will I be okay? I will not make serious error. All you have to do is take the Newtonian potential, calculate this. If this is much less than 1, Newtonian calculation is all right. So for a sun, you can calculate 2 phi by c square is much, much less compared to 1. Only when you go to white dwarf, neutron stars, on the surface of a white dwarf, surface of a neutron star, 2 phi by c square will start dominating. So for example, do this numerical calculation. A neutron star having mass 1.4 solar mass has a radius 10 kilometers. Okay? Find out the following quantity. G times 1.4 solar mass divided by 10 kilometer. And how does it compare with c square by 2? You'll find that although it is less than 1, it's comparable. I mean, all I'm saying is calculate this quantity. 2 by c square multiplied by g into 1.4 solar mass divided by 10 kilometer. Okay? No, 10 kilometers is not Schwarzschild of 1. Correct. Yeah, that's dimension. As you know that for a sun's mass is 2 into 10 to the power 33 gram, and Schwarzschild radius 2 gm by c square will turn out to be 3 kilometers. Well, astrophysicist, so all these numbers are in my head. Every time I do mental calculation for astrophysical situation, so these numbers have to be in my head.
Can you just write it on the board? What thing?
Yeah, what you want me to, what I want you to compute? Yeah, so I want you to compute this quantity. 2 by c square is already there. Newtonian constant Gm times 1.4 solar mass. So solar mass is 2 into 10 to the power 33 gram divided by the radius of the neutron star, which is 10 kilometer. 1 kilometer is 10 to the power. It is 10 to the power 3 meters, so 10 to the power 5 centimeters. So people dealing with actual physical numbers, you have to know numbers. Ultimately, when you make a correspondence with measurement observation, you have to know numbers. C square. What is C in CGS unit? 3 into 10 to the power 10. So C square will be 9 into 10 to the power 20. So here is 9 into 10 to the power 20, here is 10 to the power 33. You say, why is it small? Gravitational constant. Gravitational constant is 6.7 into 10 to the power minus 8 in CGS. You'll find this is smaller than 1, but not so small. Okay? Okay, I think I must stop here. It's already close to 1:30. So are there questions? So corrections to Newtonian gravity is important when you are going close to a white dwarf. For example, redshift of iron lines, X-ray lines have been observed in the ambience of white dwarfs, neutron stars, and redshift have been observed, and from that they do determine the mass of white dwarf and mass of neutron star. Yeah, Anuj.
Turns out that even in structural metric, the G0 term is the same, even when we only.
Yeah, that's a very important point, that the H00 term. So for it, what Anuj is pointing out, that's a remarkable coincidence. These are the reasons why Newtonian gravity works. If those coincidences wouldn't have happened, Newtonian gravity wouldn't have worked, but general relativity is a very different theory. General relativity, gravity is not a force, and yet Newtonian gravity works. One of the main reasons why it works is that if you take that's what Carl Schwarzschild exact solution. If you take a spherically symmetric mass distribution, it turns out G00 is exactly equal to 1 minus 2g mass of the object by c square r. And Gm by r is Newtonian potential. So because the Schwarzschild spacetime is almost close to what happens in Newtonian approximation, that Newtonian gravity works. Otherwise, they would depart from general relativity.
What happens if we don't take those terms as graviton?
So those are the post-Newtonian calculations. So you can, I gave you one result, right? I gave you a result that post-Newtonian calculation, the acceleration due to a blob having energy density E, pressure, what kind of modification comes about. So when you include post-Newtonian corrections, you'll get those results.
Contribution to phi, or will you play?
So H0i will be producing gradient of H0i will produce a gravitomagnetic effect. In fact, any rotating object, it causes frame dragging. The frame dragging, the sort of the probe B, the gyroscope experiment, Stanford gyroscope experiment, that was probing the effect of H0i because Earth is rotating. So those effects, frame dragging effects, will be contributed by H0i. By the way, Bhashwati has left. I think one tutorial problem must be constructed to see that a satellite, take a circular orbit satellite. Yeah, take a geosynchronous. A geosynchronous satellite will be necessarily in the equatorial plane. So take a geostationary satellite going around Earth. So it is moving and is also in the gravitational field of Earth. You can show the proper time of a clock which is at rest in this geosynchronous satellite. Its proper time is not same as the proper time of a clock on the surface of the Earth, because it is moving and it's in a different gravitational field. The clock on the Earth is in a stronger gravitational field. So clock on Earth, if you take identical atomic clocks, the clock on Earth is ticking at a slower rate compared to clock far away, but it is also moving. So you have to also do special relativist time dilation. You'll find all these corrections have to be made in order that the clock on the geosynchronous satellite is, synchronous with the clock on the Earth. Unless you do the corrections time and again, your GPS will not give you directions. So one of the practical application of GR is finding out locating direction using GPS. If you don't do these two corrections, special relativistic as well as this H00 calculation, your GPS satellite will not give you the correct position.